My dear students, if you guys remember, we discussed a passive circuit element in the previous class, that is resistor. We discussed Ohm's law as well. And with the help of Ohm's law, we can find out the voltage drop across the resistor, the current in the resistor, the power taken by the resistor from the voltage source, and the power supplied by the voltage source. We are going to discuss another passive circuit element today, and this passive circuit element is known as capacitor. Capacitor is also known as energy storing element because it stores the electrical energy in its electric field. So capacitor is also known as energy storing element. How do we make a capacitor? So a capacitor consists of two metallic plates. The area of the metallic plate of the capacitor is represented by A. There is a dielectric material between the two plates of the capacitor, and the relative permittivity, which is also known as the dielectric constant of the dielectric material, is represented by epsilon r. We may use air as a dielectric material as well, and we know that the dielectric constant of the air is 1. The distance between the two plates of the capacitor is represented by d. The separation between the two plates of a capacitor is represented by d. So if we want to find out the capacity or the capacitance of a capacitor, we can find out the capacitance of a capacitor with the help of this particular equation. There are 3 parameters. A is the area of one of the two metallic plates of a capacitor. Epsilon is the permittivity of the dielectric material between the plates of a capacitor. And D is the separation between the two plates of a capacitor. So if you guys want to increase the capacitance of a capacitor, you guys can increase the capacitance of a capacitor by varying these 3 parameters. You guys can increase the cross-sectional, the area, not the cross-sectional, but the area of the metallic plate. You guys can increase the permittivity of the dielectric material between the two plates, or you guys can decrease the separation between the two plates of the capacitor. Now let us consider this simple circuit. In this simple circuit, we have applied a time varying voltage across the capacitor. Capacitor is a passive circuit element. So we have applied a time varying voltage across this passive circuit element. Whenever we apply some voltage across a passive circuit element, the voltage across the passive circuit element results in a current. And the nature of the current depends upon the nature of the applied voltage. If usually the nature of the current depends upon the nature of the applied voltage. If the magnitude of the voltage is constant with respect to time, then the current in the circuit is constant with respect to time. And if the magnitude of the voltage of the applied voltage varies with time, then the magnitude of the current varies with time as well. So there will be a current in the passive circuit element, there will be a current in this capacitor. This current will be known as instantaneous current. Why? Because the magnitude of this current will change with respect to time. And you guys can find out the magnitude of this current, the value of this current at any time, at any instant. Whenever there is a current in a passive circuit element, the current in a passive circuit element results in a voltage drop. So the current in this passive circuit element will result in a voltage drop. You see, we apply KVL to this loop. And the current in this loop is in the clockwise direction. Keeping in view the direction of the current through the voltage source, you see the current flows from the negative terminal of the voltage source towards the positive terminal. The voltage across the source is known as a voltage rise. As the current flows from the negative terminal of the voltage source towards the positive terminal, so the voltage across the source is a voltage rise. We consider the direction of the current through the capacitor of this simple series circuit, and this current flows from the plus polarity of this voltage towards the minus polarity. So this voltage is a voltage drop. So the voltage across the source is a voltage rise, and the voltage across the capacitor is a voltage drop. We apply KVL to this loop, Kirchhoff's voltage law. And Kirchhoff's voltage law states that sum of the voltage rises in this loop will be equal to sum of the voltage drop. The voltage across the source is a voltage rise, and the voltage across the capacitor is a voltage drop. So the voltage across the source in this particular case will be equal to the voltage across the capacitor. So we develop this relationship with the help of KVL. The voltage across the source in this particular circuit is equal to the voltage across the capacitor. So as the current is moving towards the capacitor, and what is current? You know that current is the motion of charge in a circuit. This means that the charge is moving towards the capacitor. and this charge will accumulate on the plates of the capacitor. So we know that the charge on the plates of the capacitor, depends upon the voltage across the capacitor. The charge on the plates of the capacitor is directly proportional to the voltage across the capacitor. If you increase the voltage across the capacitor, the charge on the plates of the capacitor will increase linearly. So we can say that there is a linear relationship between the voltage across the capacitor and the charge on the plates of the capacitor. So the charge on the plates of this capacitor, of this passive circuit element, is directly proportional to the voltage across the capacitor. By decreasing the voltage across the capacitor, the charge on the plates will decrease linearly. The constant of proportionality in this particular case is the capacitance of this passive circuit element, which is represented by C, and we know that the unit of the capacitance is farad. So the charge on the plates of the capacitor will be equal to CVC. So if you guys want to find out the time varying charge on the plates of this passive circuit element, you guys can find out the charge on the plates of this passive circuit element with the help of equation number 1.15 with the help of equation number 15. Now what we do, we differentiate both sides of equation number 15 with respect to time. We know that the charge on the left hand side is a time varying charge. The magnitude of the charge on the plates of this capacitor varies with time. It's a time varying charge. Similarly, the voltage across the capacitor is a time varying voltage. The voltage across the capacitor varies with time as well. So what we do, we differentiate both sides of equation number 15 with respect to time. So we differentiate the charge on the left hand side with respect to time, and we differentiate the voltage across the capacitor with respect to time. So dq by dt is equal to C into dvc by dt. And we know that the rate of motion of charge is known as current. So dq by dt represents the current in the capacitor. So the current in the capacitor will be equal to C into the derivative of the voltage across the capacitor with respect to time. This is how we calculate the voltage, this is how we calculate the time varying current in the capacitor. You see, if we apply a DC voltage across the capacitor, according to KVL, the voltage across the source in this particular circuit will be equal to the voltage across the capacitor. So the voltage across the capacitor in case of a DC voltage source will be a constant voltage. And if you guys want to find out the current in the capacitor in this particular case, the derivative of the constant voltage with respect to time will be 0. So dvc by dt will be equal to 0, and this means that the current in the capacitor will be 0. So whenever we apply a DC voltage, across a capacitor, the capacitor blocks the DC current. There will be no flow of DC current in the capacitor. The capacitor always blocks the DC current. It offers infinite resistance to the flow of DC current. This is a very important characteristics of the capacitor, as it blocks the DC current. And you guys will study these characteristics, the application of the capacitors with respect to these characteristics in the course of electronics. You see, you guys will study different transistor configuration, common base amplifier, common collector amplifier, common emitter amplifier, and if you guys want to block, you see, the DC component of the signal, then you guys will have to use a capacitor to block the DC component of the signal, the DC component of the current, the DC component of the voltage. So anyhow, just keep it in your mind that capacitor blocks the DC current. It does not allow the DC current at all. Anyhow, if you guys want to calculate the time varying current in a capacitor, you guys can use equation number 17 and you guys can find out the instantaneous current in the capacitor with the help of equation number 17. Now what I am going to do, I'm going to develop the equation for the voltage across the capacitor in terms of current. You know what I am saying? I mean to say that if the current in the capacitor is known and you guys want to find out the time varying voltage across the capacitor, what you guys will do? So we are going to find out the equation for the voltage across the capacitor. In order to find out the equation for the voltage across the capacitor, let us play with equation number 17. So we play with equation number 17. We play with equation number 17. So, we can write down equation number 17 in terms of equation number 18. DVC represents the differential voltage. So the differential voltage across the capacitor will be equal to 1 over C I dt. I obtained equation number 18 with the help of equation number 17. I hope that this equation will be clear to you guys. Now what is the differential voltage? Or what is the differential time? The differential voltage is represented by dV. This voltage is known as differential voltage. The differential time is represented by dt. So let me explain the differential voltage and differential time. What I do, I consider a line over here, and the total length of the line is L. L represents the total length of this line. And I divide this line into a very large number of very small segments. I divide this line into a very large number of very small segments. Each small segment is represented by dl. This is a very small segment of this line, and this segment is so small. Let me give you the example of this differential length. You see, it might be in terms of 2 into 10 raised to power minus 5 meter. It might be in terms of 2 into 10 raised to power minus 6 meter, or 2 into 10 raised to power minus 7 meter. So this segment is a very small segment. So if you guys want to find out the total length of this line, you guys need to add all these differential lengths. So we have dl plus dl plus dl and so on plus dl. So we add all the differential lengths along this line, and the summation of all the differential lengths of this line gives you the total length of this line. So dl basically represents a very small portion of the length of this line, a very small segment of the length of this line. And if you focus on the right hand side of this equation, the summation of the differential length in mathematics is represented by this integration. The integration of dl means that we add all the differential lengths of this line, and the summation of all the differential length of this line gives you the total length of this line. So what is differential length? Differential length is a very, very small segment of the total length. Similarly, I have differential voltage over here. So this is a very small portion of the total voltage across the capacitor. Let's say that the differential voltage across the capacitor is 10 raised to power minus 6 volt. Let's say this is the differential voltage across the capacitor, a very small portion of the total voltage. So it means that, well, if the total voltage across the capacitor is 1 volt, this is just an example. If the total voltage across the capacitor is 1 volt, and we have selected the differential voltage, a small portion of this voltage, which is 10 raised to power minus 6, then it means that we have divided the total voltage of this capacitor into 10 raised to power 6 numbers of very, very small portion, which will be equal to 1 volt. So what is the differential voltage? Basically, we divide the total voltage of the capacitor into we divide the total voltage of the capacitor into a very large number of very, very small portion, and this small portion is represented by the total voltage, the differential voltage. Similarly, what is the dt? dt is a very small portion of the total time, right? Let's say the total time is 1 second. This is just an example to understand the differential quantity. You see, let's say the total time is 1 second, and the differential time is 1 microsecond, that is 1 into 10 raised to power minus 6. This means that we have divided the total time into 10 raised to power 6 segments, which results in 1 second. So you see, we have divided the total time into a very large number of very, very small segments. So if you divide you see a quantity into a very large number of very, very small portion, a small portion will be known as differential quantity. So anyhow, this is how we calculate the differential voltage across this passive circuit element. We are not interested in the differential voltage. We are interested in the total voltage. So if I want to find out the total voltage across the capacitor, I need to integrate equation number 18, and the integration of equation number 18 will give you the total voltage across the capacitor. So you guys can calculate the total voltage across the capacitor with the help of equation number 19. So the total voltage across the capacitor will be equal to 1 over C into the integration of I dt. Okay. Now, let us go back to the circuit. We go back to this particular circuit. There are two circuit elements in this particular circuit. The capacitor, which is a passive circuit element. Capacitor is known as a passive circuit element because it takes the energy from the voltage source. And the voltage source which delivers energy to this particular circuit. So there are two circuit elements in this particular simple circuit. The active circuit element, which is the voltage source, and the passive circuit element, which is so there are two circuit elements in this simple circuit. The voltage source is known as active circuit element because it delivers energy, while capacitor is known as passive circuit element because it takes the energy from the voltage source. So according to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the capacitor. According to the law of conservation of energy, the power supplied by the voltage source will be equal to the power taken by the capacitor. So if we want to find out the power supplied by the voltage source, we can find out the power supplied by the voltage source with the help of this product. The product of the voltage across the source and the current in the source will give you the power supplied by the voltage source. And the power taken by the capacitor will be equal to VCI. So what we do, we know that the current in the capacitor is basically equal to C into dVc by dt. This is how we calculate the current in the capacitor. We put this value of current in equation number 21. So the power taken by the capacitor will be equal to CVC into dVc by dt. This is the power which is taken by the capacitor from the voltage source. And we simplify equation number 22. Please focus on equation number 22. You see, we play with equation number 22. We will get PC into dt on the left hand side of equation number 22, which is basically differential energy. So the differential energy, which is equal to PC into dt, will be equal to CVC into dVc. So we use equation number 23 to find out the differential energy which is taken by the capacitor from the voltage source. We are not interested in the differential energy. Why? Because differential energy is a very small portion of the total energy. So I am not interested in a very small portion of the total energy. I am interested in the total energy of the capacitor. How much energy is taken by the capacitor from the voltage source? So if the differential energy is known, you guys can calculate the total energy with the help of the integration of the differential energy. So what we do, we integrate both sides of equation number 23, which gives you the which gives you the total energy, taken by the capacitor from the voltage source. So the integration results in equation number 24. The total energy which is taken by the capacitor from the voltage source will be equal to 1 over 2 into C Vc square, and keep it in your mind that in this particular case the voltage across the capacitor is equal to the applied voltage. So we can find out the total energy with the help of equation number 24. This is how we calculate the total energy. Let us talk about another passive circuit element which is known as inductor. We shall talk about Faraday's law in this particular topic as well. So what is an inductor? Inductor is basically a coil of n number of turns. And you know that a coil is made of a conductor. So how do we make an inductor? If you guys want to make an inductor, you guys need to have a conductor. Even a simple straight conductor behaves like inductor as well. But the inductance of this simple straight conductor will be less than the inductance of the coil, because coil has n number of turns. So if you guys want to make an inductor, you guys can make a winding or a coil of n number of turns from the conductor. When you make a coil of n number of turns from the conductor, this coil is known as inductor. So you see, the symbol of an inductor is shown in figure number 1.7. Figure number 1.7 gives you the symbol of an inductor. Let us apply a time varying voltage across this passive circuit element. Inductor is known as passive circuit element. Why? Because inductor takes energy from the voltage source. So any circuit element which takes the energy from the voltage source is known as passive circuit element. Inductor is a passive circuit element. Why? Because it takes energy from the voltage source. Inductor is known as energy storing element as well. Why? Because inductor stores energy in its magnetic field. Whenever you apply some voltage across a coil, इसकी मैग्नेटिक फील्ड में बहुत ज़्यादा एनर्जी आ जाती है और इस एनर्जी को ऑब्जर्व करने के लिए क्लास में मैं एक मिसाल देता हूं. I cannot give you that particular example right now because you guys cannot see me. So you guys can ask me this question during the online session and I will explain this magnetic energy. And I will ask you guys in the online session to do a very simple experiment and feel this energy. So inductor stores this energy in its magnetic field. So this passive circuit element is also known as energy storing element. So what we do, we apply a time varying voltage across this passive circuit element. The voltage across the source is represented by Vs. Whenever we apply some voltage across any passive circuit element, the application of the voltage across a passive circuit element results in a current. So definitely there will be a current in this passive circuit element which is represented by I. And whenever there is a current in a passive circuit element, the current in a passive circuit element results in a voltage drop. So the current in this passive circuit element results in a voltage drop. And let me repeat another statement over here. Usually the nature of the current in any passive circuit element depends upon the nature of the applied voltage. If the voltage is constant with respect to time, the current in the passive circuit element will be constant with respect to time. And if the voltage varies with time, then the current in the passive circuit element will vary with time. Anyhow, we apply KVL to this loop. And the current in this loop is in the clockwise direction. Keeping in view the direction of this current, the voltage of the voltage source is a voltage rise. Why? Because this current flows from the negative terminal of the voltage source towards the positive terminal. Keeping in view the direction of this current in the inductor, the voltage across the inductor is a drop. Why? Because the same current flows from the plus polarity of this voltage towards the minus polarity. So there is only a single voltage rise in this loop and only voltage drop. We apply KVL to this loop. KVL states that sum of the voltage rises in this loop will be equal to sum of the voltage drops. So the only voltage rise in this loop will be equal to the only voltage drop in this loop, and the voltage across the source in this particular case will be equal to VL. So we consider a passive circuit element over here, which is known as inductor. Inductor is basically a coil of n number of turns. So n is constant. N represents the number of turns of the coil, which is constant. Well, the inductance of this inductor will be constant as well. Okay, the number of turns will be constant. Let's see, represents a constant, and the inductance of this inductor will be constant as well. Let me represent this constant by C2. Well, we know that whenever there is a current in a coil, magnetic field is generated. If the current varies with time, the strength of the magnetic field will vary with respect to time. And if the current is constant, then the magnetic field in the vicinity of this inductor will be constant. So the current in this coil generates a magnetic field. In other words, the current in this coil generates magnetic flux, which is represented by phi. And the magnetic flux, which is generated by the current in this coil, depends upon the current in the coil. By increasing the current in the coil, the magnetic flux will increase. And by decreasing the current in the coil, the magnetic flux will decrease. So we just want to write down this relationship in the form of an equation. It means that the magnetic flux will be equal to L by N, which is a constant, into I. So L by N in this particular case is the constant of proportionality. So the magnetic flux, which is generated by the current in this inductor, will be equal to L by N into I. What is L? The inductance of this passive circuit element. What is N? The number of turns of the coil of this passive circuit element. And definitely I represents the current. So the magnetic flux, which is generated by the current in this inductor, will be equal to L by N I. And we can find out the equation for the inductance from this equation. The inductance of the inductor will be equal to N phi by I, where N represents the number of turns of the inductor, the number of turns of this coil, the number of turns of this winding. Coil is also known as a winding. And if I have a straight conductor, N will be equal to 1 for a simple straight conductor. If there is a current in this conductor, this simple straight conductor will behave like inductor, and the inductance of the simple straight conductor will be equal to phi divided by I. Why? Because n in this particular case is 1. So the inductance of a simple straight conductor can be calculated with the help of this particular equation. So even a simple straight conductor behaves like inductor as well. Whenever a current flows in a simple straight conductor, magnetic field is generated in the vicinity of the conductor. Magnetic flux is generated. Even if you make a coil of 1 turn from this simple straight conductor, n will be equal to 1 in this particular case as well. So n will be 1 if you make a coil of 1 turn from the straight conductor, or if you leave it as a straight conductor. So कहने का मकसद ये था कि even a simple straight conductor behaves like inductor, but the inductance of a simple straight conductor is less than the inductance of a coil. So you see, let us consider the first equation of this particular slide, and let us write down this equation in this form. So the first equation of the previous slide can be written as, we have n, which is the number of turns of the inductor, into phi, which is the magnetic flux generated by the current, into Li. Let me call it equation number A. So we consider this equation now. You see n on the left hand side is constant. N on the left hand side is constant. Phi is varying with respect to time. L on the right hand side is constant. And I is a time varying current. So what we do, we differentiate both sides of this equation with respect to time. If we differentiate both sides of this equation with respect to time, we have n d phi by dt, which is equal to L di by dt. And now we focus on the left hand side of this particular equation. Let us focus on the left hand side of this particular equation. In this particular circuit, we have got an inductor of n number of turns. There is a current in this inductor which is represented by I. This current generates a magnetic field in the vicinity of this coil, which is represented by phi. The nature of the magnetic flux depends upon the nature of the applied voltage. If the current is constant with respect to time, the magnetic flux will be constant with respect to time. And if the current varies with time, then this magnetic flux will vary with respect to time. So this magnetic flux is varying with respect to time. So this inductor is located in its own time varying magnetic field. We recall Faraday's law. Faraday's law says that whenever we place a coil in a time varying magnetic field, voltage is induced across the coil. So according to, and this voltage is known as self-induced voltage. This is not a mutual induction. This is self-induction. So according to Faraday's law, the time varying magnetic flux will induce some voltage across this passive circuit element, which is represented by VL, and VL will be equal to N d phi by dt. So we replace the left hand side of this particular equation by VL in accordance with Faraday's law. Faraday's law states that whenever we place a coil of n number of turns in a time varying magnetic field, voltage is induced across the coil. This is how we induced a voltage in this particular coil, which is known as a self-induced voltage. So we replace the left hand side of this particular equation by VL in accordance with Faraday's law. It means that VL will be equal to L di by dt. So the time varying voltage across an inductor can be calculated with the help of equation number 29. The voltage across the inductor, the time varying voltage across the inductor will be equal to L di by dt. We have the derivative of the current with respect to time on the right hand side. If I apply a DC voltage across the inductor, if I apply a DC voltage across the inductor, there will be a DC current over here, and according to this particular equation, the derivative of the constant current will be equal to 0, so there will be no voltage drop across. There will be no voltage drop across the inductor if there is a DC current in the inductor. The inductor does not offer any resistance to the flow of DC current. Practically, it offers a very small resistance to the flow of DC current. Anyhow, this is how we calculate the time varying voltage across the inductor. Now let us focus on the current. You see, di from equation number 29 will be equal to 1 over L into VL dt. This is the differential current in the inductor of this particular circuit. And what is the differential current? A very small portion of the total current. So we are not interested in the differential current. We are interested in the total current. So for the total current, we integrate both sides of this particular equation, which gives you the time varying current in an inductor. So you guys can calculate the time varying current in an inductor with the help of equation number 30. This is how we calculate the instantaneous current or the time varying current in an inductor. Let us go back to the circuit diagram. You see, there are two circuit elements in this particular circuit. The voltage source, which is known as active circuit element. Why? Because it delivers energy to the remaining circuit. Inductor, which is known as passive circuit element, because this inductor takes the energy from the voltage source. So source delivers energy to the inductor, and the inductor takes this energy from the source. According to the law of conservation of energy, the power supplied by the source will be equal to the power taken by the inductor. So the power supplied by the voltage source will be equal to the power taken by the inductor. This is in accordance with the law of conservation of energy. the law of conservation of energy states that the power supplied by the voltage source will be equal to the power taken by the inductor. We know that the power supplied by the voltage source will be equal to the voltage across the source multiplied by the current in the source, and in this particular case Vs is equal to Vl. So the power supplied by the source can be calculated with the help of any one of these two equations. So we can calculate the power, either the power supplied by the voltage source or the power taken by the inductor, with the help of this particular equation. And we put the value of VL in equation number 32, because VL is equal to L di by dt. So let us put the value of VL in equation number 32. If we put the value of VL in this particular equation, the power taken by the inductor will be equal to L dLi into di by dt. We play with this particular equation. On the left hand side, we get PL into dt, and we know that PL into dt is the differential energy which is taken by the inductor from the voltage source, and PL into dt will be equal to L I into di. This is the differential energy which is taken by the inductor from the voltage source. We are not interested in the differential energy. We are interested in the total energy. So if we are interested in the total energy will be equal to, you see, as dW is the differential energy, and this differential energy is equal to Li into di. So we integrate both sides of this equation. So the integration of both sides of this equation gives you the total energy which is taken by the inductor from the voltage source. So in this particular class we have discussed two passive circuit elements, capacitor and inductor. How do we calculate the current in a capacitor? How do we calculate the voltage across a capacitor? How do we calculate the power in a capacitor? How do we calculate the energy stored by a capacitor? And so on. So thank you so much. If you guys have any question, I shall respond to your questions in the online session.